This section is going to focus on section 6.2, linear and almost linear systems. Before we dive in, let's talk a little bit about where we've been as well as where we're headed. In chapter 5, we dedicated a lot of time to learning how to solve systems of differential equations, specifically linear systems. And we use the method of eigenvalues and eigenvectors to help find those solutions. In 6.1, we focused on identifying critical points as well as classifying those critical points. So we could classify them by type in terms of node, center, saddle, etc., spiral. And then we also classified them in terms of stability. Are they stable, asymptotically stable, unstable? In section 6.2, we're going to also talk about how to classify critical points in linear systems, as well as how to handle almost linear systems. These are nonlinear systems that are nearly linear. How are we going to handle that, as well as classify critical points? So to get started here, I just want to remind everybody how to find a critical point of an autonomous system. So in order to find a critical point, we're utilizing this equation here, where we want to set each of the functions f of x, y, and g of x, y equal to 0. And if they're simultaneously 0 at a given point, x naught, y naught, then that point is considered a critical point. So I have a little remark here that says, look, we could, without loss of generality, just assume that a critical point is 0, 0. Because if it wasn't at the origin, we could translate the entire system over a certain amount of x values and y values until a given critical point is at the origin. So quite often we'll talk about classifying the critical point 0, 0 because we can do this translation. One more remark here says that we will use the eigenvalue method to classify the critical point 0, 0 of the 2 by 2 system. So we're going to rely on our knowledge of the chapter 5, finding eigenvalues, in order to identify the classification of each critical point. So here at the bottom of page 1, I have just an overview of how we're going to classify these critical points. Here we are assuming that lambda 1 and lambda 2 are eigenvalues, and we're going to classify in the following way. So case 1 is that we have real and unequal eigenvalues, but with the same sign. Real and unequal with the same sign. If they're positive, then we have a source. And if they're negative, we have a sink. Number 2 says, well, what happens if they're real and unequal with opposite signs? So the moment you see opposite signs, you don't need to look any further, then you know that it's a saddle point. And we know that saddle points are always unstable. So they just specified there that if it's a saddle point, it's necessarily unstable. All right, so what happens if they're real and equal? This is the only case that requires additional work. So real and unequal, you have to check the eigenvalue, or sorry, real and equal, you need to compute the eigenvalue vectors. Compute eigenvectors to determine complete versus defective. All right, so part A under case 3 says that if they are equal and complete, then it is either a proper node or a star. And so here it shows if they're positive, that node is a source, and if they're negative, that node is a sink. Now, if they're defective, remember what that means. It means that you are not admitting enough linearly independent eigenvectors. Then it's an improper node. So here again, if they're positive, it's a source. If they're negative, it's a sink. So this is the only case where you need to go past computing the eigenvalues and compute those eigenvectors just to determine which case you're in. And then we have 2 different cases for complex pairs. If they're complex conjugates that include real and imaginary portions. So you can see here this clause at the end that P and Q are necessarily non-zero. Then it's a spiral. If your real portion is positive, then it's a source. If the real portion is negative, it's a sink. And if you get purely imaginary conjugates, Here, notice that P is equal to 0. The real portion vanishes. Then you have a stable center. Here again, centers are always stable, so you don't need to check for stability in that case, just as saddle points are always unstable. I am not going to require my students to memorize this. So on quizzes and exams, I will provide you with the table that has this information in it. And so I will discuss what that table is going to look like here later on in the lecture. So the previous set of instructions told us how to classify the type of critical points. And in certain cases, we got the stability for free in the sense of when we were talking about centers and saddles, but for the other ones, we really weren't able to identify the stability type. So theorem 1 here says, let lambda 1 and lambda 2 be eigenvalues of the coefficient matrix. And I'm going to assume that AD minus BC is non-zero. This is just the determinant of the coefficient matrix, which we generally denote by A. All right, then the critical point is the following. It is asymptotically stable if the real parts are both negative. It is stable but not asymptotically stable if the real parts are both 0. In other words, you get the purely imaginary complex conjugates, and it's unstable if either of the eigenvalues has a positive real part. All right, so positive real, automatically you get unstable and you don't need to look any further. All right, so let's take a look at some examples of classifying critical points. Number 4 from the textbook says, determine the type of critical point 0, 0 for the given system and classify its stability. All right, so what I'm going to do is I'm going to set up my characteristic equation, which is going to be the determinant of A minus lambda I. So I'll fill that in. And I want to set that determinant equal to 0. This is the definition of the characteristic equation. So this becomes 3 minus lambda times negative 1 minus lambda minus 5 equals 0. If we expand this out, we get lambda squared. I have a positive 3, or excuse me, a negative 3 and a positive 1 gives me a negative 2 lambda. And then I have a negative 3 minus 5 is a negative 8 equals 0. So this factors to x minus 4, excuse me, lambda minus 4, lambda plus 2. And so for my eigenvalues, I get 4 and negative 2. All right, so at this point, I should be able to classify both the type and stability of this critical point. All right, so let's look up. We have real n-equal eigenvalues. One is positive and one is negative. All right, real and unequal with opposite signs. We are looking in case 2. One is positive, one is negative. We need to look no further. This is an unstable saddle. This portion here gives us both the stability and the type. So I'm just gonna clarify here, 0, 0 is an unstable saddle. Okay. So we didn't even need to use theorem 6.2.1 because again, saddles are always unstable. So let's do the exact same thing here for problem 10. I'll set up my characteristic equation. That is the determinant of 1 minus lambda, negative 2, 5, negative 1 minus lambda equal to 0. So let's see what we get here. We get 1 minus lambda times negative 1 minus lambda plus 10 equals 0. So this is lambda squared. I get a positive lambda and a negative lambda. Those are canceling. Minus 1 plus 10 is a plus 9. So here I'm getting lambda equals plus or minus 3i. So I'm getting a purely imaginary complex conjugate pair. And now I'd like to classify the type and stability here. So let's move on up to page 1. When we have purely imaginary, we are in case 5. And here again, it just tells us that this is a stable center. So I'm going to copy this down 0, 1 is a stable center. Now, if we went up to theorem 1, notice here that we are in case 2, where we have these purely imaginary complex conjugate pairs. So the real portions are 0. So we can specify here, this is stable, but not asymptotically stable. So I'll just add that in for clarification, but not asymptotically stable. All right. So there's a couple of examples of working with eigenvalues to classify critical points. Again, pretty straightforward as long as you have those, the theorem and classification. All right, so what I'd like to do here is just recall the Jacobian matrix, which we've seen before in Calc 3, but perhaps you're a little rusty. So recall that given two multivariable functions, f of xy and g of xy, the Jacobian matrix of f and g is given by the partials of f with respect to x and y across the top row, and the partial of g with respect to x and y across the bottom row. So the partials with x are always in the first column. The partials with respect to y are always in the second column. So we've used the Jacobian in Calc 3 when we were doing transformations of various coordinate systems. And so we're now going to use the Jacobian to help us with nonlinear systems. So I have a definition here. Given a nonlinear or an almost linear system, its linearization at x naught, y naught is the following. So this is a very important equation here. We are switching from an x system. Normally we write x prime equals a x to this u system. U prime equals the Jacobian evaluated at x naught, y naught times u. Here where this Jacobian matrix is going to be evaluated, and they're saying that u is the that should say transpose or inverse of uv. So in other words, let's write it like this: u is uv. All right, where normally we're working with x, which is x, y, or sometimes we've been working with x1, y1. All right, so just as we used it in Calc 3 as a change of variables, we're doing a similar thing here in differential equations. We're going to switch from a nonlinear system in x and y to an associated linearization or a linear system in u and v. But in order to make that transformation, we pay for it with the Jacobian. So let's take a look at an example. First, we just want to practice finding the linearization. So we have this clearly nonlinear system. Right? We have some squareds here. We also have products of x and y, which also make it nonlinear. And we would want to find the associated linearization. So to begin, let's find the Jacobian at xy. So that is the matrix where the top row is going to be the partial of, let's call this one up here, f of xy. So I want to take the partial of f with respect to x. That's going to give me 1 plus 0 minus y squared. And then in the first row, second column, that'll be the partial of f with respect to y. So 0 plus 4 minus 2xy. And now across the bottom row, I want the partials of g, where g of xy is given by that y prime equation. So the partial of g with respect to x is 2 minus 0 plus 2xy. And the partial with respect to y is negative 1 plus x squared. All right, so this is my Jacobian matrix that's associated to this nonlinear system. And now I would like to evaluate the Jacobian at the point that they gave me, in this case, 0, 0. So my Jacobian at 0, 0, anything with an x or y is going to die. So I just get my constants 1, 4, 2, negative 1. And you'll notice here that those are exactly the coefficients of the linear terms. Now, that only happened because we were evaluating at 0, 0. Had we been evaluating at some non-zero point, we would have gotten additional terms in there. And so now let's go ahead and write out the system. We started with the given nonlinear system, and the linearization is now u prime equals u plus 4v, and v prime equals 2u minus v. So all I'm doing at this point is using this Jacobian and looking at this as u prime equals the Jacobian times u. And I'm just writing it out in its scalar notation. All right, so that's just an example of how to find a linearization of an almost linear system. And so our goal here is to take these nonlinear systems and be able to classify the critical points. We cannot solve these nonlinear systems by method of eigenvalues and eigenvectors because that only works for linear systems. So our plan here is to take a nonlinear system, to linearize it in this method, and then look at the critical points and classify according to that. So we have theorem 2 here that says, let lambda 1 and lambda 2 be the eigenvalues of the coefficient matrix of the linear system associated with a given almost linear system. So we're looking at this associated linear system, exactly what we just found in 22. And we have 3 cases. If lambda 1 and lambda 2 are equal real eigenvalues, then the critical point 0, 0 of the almost linear system is either a node or a spiral point. So we cannot for sure say which is which. And it is asymptotically stable if lambda 1 equals lambda 2 is negative. And it is unstable if they're both positive. All right, so again, I just want to specify that we can't for certain identify whether it's a node or a spiral point. So in these circumstances, I just want you to list the possibilities. If you fall into this category, say it's either a node or it's a spiral point, and you really just can't identify unless you're looking at the phase portrait, in which case you can just visually identify whether it's a node or a spiral. Case 2, if lambda 1 and lambda 2 are purely imaginary, then it's either a center or a spiral point. Again, we can't clarify which. And really, we have no idea on the stability. It just says it could be asymptotically stable, stable, or unstable. We're hosed in this case. So again, unless you have the phase diagram and you can physically see, are the arrows pointing inward or outward or what's happening, we just can't say algebraically. Finally, if it's neither of those cases, then it falls into the category of the associated linear system. So you're just going to look at your eigenvalues and potentially your eigenvectors, if you fall into that category, and classify according to the linear system. All right, so let's take a look back at 22. We had just looked at the linearization of this system. And so I'll just recall here that what we had was u prime equals u plus 4v, and v prime equals 2u minus v. This was the associated linear system to the given nonlinear system. And we want to investigate the type of critical point. So what we're going to do is we're going to proceed just as we were doing with the linear ones. Let's start up with our characteristic equation, which is 1 minus lambda, 4, 2, and negative 1 minus lambda, and equate that to 0. Computing the determinant, I get 1 minus lambda, negative 1 minus lambda, and then I get a minus 8 equals 0. So I get lambda squared. I have a positive lambda and a negative lambda cancel. Then I get a negative 1 and a negative 8 is minus 9 equals 0. So here what I'm getting is my eigenvalues are plus and minus 3. They are real and distinct, and they have opposite signs. So let me just zoom out a bit here so that we can see theorem 2. We are not in case 1. These are not real and equal. We are not in case 2. These are not purely imaginary. So that means we're just going to go back up to the linear system classification. And if you'll recall, when we had a positive and negative eigenvalue, whenever they straddle 0, that's a saddle point. And so we are just going to conclude here that 0, 0 is an unstable saddle. All right. And so here, this table really nicely summarizes what Theorem 2 says, including all of the old linear stuff and then the new linearized stuff. So here, the first line, if both of your eigenvalues are negative, you have a stable improper node. If they're equal and negative, you have a stable node or a spiral point. Again, we can't classify which. If they're straddling 0, we have an unstable saddle. That's what we just had in 22. If they're equal and positive, we have either an unstable node or a spiral point. If they are unequal and positive, we have an unstable improper node. And then the last 3 are dealing with complex conjugate pairs. If you have complex conjugate pairs with a negative real portion, that's a stable spiral. Positive real portion is an unstable spiral, and purely imaginary, we're not certain. It's either stable or unstable, and it's either a center or a spiral point. So this table will be given for nonlinear systems for you guys to use. You are in charge of being able to identify the eigenvalues and then read off the table what your classification should be. So let's do a full example of a nonlinear system. First of all, it says find all critical points of the system and investigate the type of stability of each. I just want to emphasize here that this term in X prime is what leads us to recognize that this is nonlinear, because when we have a product of X and Y, that makes for a nonlinear function. So to begin, let's go ahead and find the critical points. Remember, to find critical points, you set each of those functions equal to 0. So our first function gives us xy minus 2 equals 0. Our second function gives us x minus 2y equals 0. So I'm going to solve for x in the second equation, that's 2y. And if I plug it into the first, I get 2y times y minus 2 equals 0. In other words, 2 times y squared minus 1 equals 0. So we get y equals plus minus 1. And then based on that, remember we have that x equals 2y. So if y equals 1, x equals 2. So we have the critical point 2, 1. If y equals negative 1, x equals negative 2. So we have the critical point negative 2, negative 1. Now here you'll notice that our critical points are not the origin. We're not going to worry about translating. We're just going to take those critical points at face value, and we would like to classify. So what is the type, and also what is the stability of this critical point? So to begin, let's compute the Jacobian. I'm going to clean up my notation up top so that we can see our system a little bit better. So the Jacobian in X and Y is the following. So for our top row, we want the partials of the X prime function. So the partial with respect to X is Y, and the partial of the X prime function with respect to Y is X. And then similarly for the bottom row, we get 1 and negative 2, since that one happens to be linear. So we have our Jacobians. Now let's go ahead and evaluate our Jacobian at each critical point. So I'll begin at 2, 1. So I'm getting out 1, 2, 1, negative 2. And now let's go ahead and compute the characteristic equation. So we get 1 minus lambda, 1, 2, and negative 2 minus lambda equals 0. Let's flush out that characteristic equation. 1 minus lambda times negative 2 minus lambda minus 2 equals 0. All right, so we get lambda squared. I have a positive 2 and a negative 1, leaves me with 1 lambda. And I have a negative 2 minus 2 is a minus 4. All right, so I don't believe that this is going to factor by hand. Let's throw it into the quadratic formula. Negative b plus or minus radical b squared minus 4ac is going to be a plus 16 all over 2. So what we're getting here is a negative 1/2 plus or minus square root of 17 over 2. All right, this is not imaginary. This is not imaginary. It looks kind of gross, but notice that there was no square root of a negative number, so this is real. And so what is the sign of these two values? Well, I don't exactly know what the square root of 17 over 2 is, but I know it's larger than the square root of 16 over 2. And the square root of 16 over 2 is 4 over 2 or 2. So one of these is going to be positive and one is going to be negative. So I'm just going to note that lambda 1 less than 0 less than lambda 2. We are straddling 0 for these eigenvalues, and so we know that this is going to be an unstable saddle. So 2, 1 is an unstable saddle. All right, and then we're going to do the exact same process for the other critical point, negative 2, negative 1. So when I plug that in, I get negative 1, negative 2, 1, negative 2. And so let's set up our characteristic equation. I get negative 1 minus lambda, negative 2, 1, and negative 2 minus lambda equals 0. And expand your characteristic equation, negative 1 minus lambda times negative 2 minus lambda, and then plus 2 equals 0. So here I'm getting lambda squared. I get a positive 2 and a positive 1 is positive 3. And then I have a positive 2 and a positive 2, so plus 4. All right, so here again, this doesn't appear to factor. So I'm going to put it into the quadratic formula. Lambda equals negative b plus or minus, whoops, I wrote b squared. Negative b plus or minus radical b squared minus 4ac will be minus 16 all over 2. And so we're getting imaginary numbers here, plus or minus the square root of 7i over 2. Or you can emphasize the fact that the real portion is negative by kind of splitting it up in this way. All right, so this is a complex conjugate pair. A is negative. Let's scroll back up to that table. And we are in this row right here. So we can definitively say that the point negative 2, negative 1 is a stable spiral point. Negative 2, negative 1 is a stable spiral. All right, so this final problem here is really illustrating not only how to find the critical points, but how to find the linearization, and then using that linearization to classify these critical points. Here again, in 32, we were definitively able to classify not only the type, but also the stability. But if you fall into one of the categories where it's an either or situation, write out all of the possibilities, and that's what I'll be looking for full credit. So this concludes our notes for section 6.2, and that also concludes all we're going to discuss in chapter 6. Moving forward, we're just going to look at the first couple of sections of chapter 7, which cover Laplace transforms.